Hi there, Physics 152. Let me walk you through some of the theory behind the standing waves experiment. So standing wave is created when two waves travel in opposite directions between two boundaries. Standing waves have well-defined patterns called modes, and some points on the wave called nodes with an N do not oscillate at all. And they're related to music because most acoustic musical instruments use standing waves to generate their sound and to amplify the sound. So guitars have standing waves on a string, and flutes have pressure standing waves. So we're going to be talking about pressure standing waves today. But changing the length of a standing wave changes its frequency and therefore the note that is played. Okay, and then one thing to notice is that the distance between either adjacent antinodes or adjacent nodes is lambda over 2, half the wavelength. The long, narrow column of air, such as the air in a tube or pipe, can support a longitudinal standing sound wave. Longitudinal meaning that the energy, which would be traveling in the x direction, is parallel, that direction is parallel to the oscillation direction of the particles in the medium. So a closed end of a column of air must be a displacement node. The particles can't shake in the x direction at that boundary. So the boundary condition is nodes at the ends are the same as for a standing wave on a string, fixed. However, it is often useful to think of sound as a pressure wave rather than a displacement wave. So the pressure oscillates around its equilibrium value. The equilibrium value meaning atmospheric pressure, the ambient pressure in the room. And it turns out that the nodes and antinodes of the pressure wave are interchanged with those of the displacement wave. So just looking at now the displacement wave, these oscillations, I'll step through 3 slides, 1, 2, and 3, showing what's going on with the actual particles. So right now, we are seeing that particles are at their equilibrium position at the left end. They're displaced to the right here, about a quarter of the way along. They're at their equilibrium position at the middle, and they're displaced to the left over at 3/4 of the way across. And so here we have a compression in the middle and rarefactions at the end. So this will be highest pressure at the center and lowest pressure at the ends. And then you have uniform pressure across when every particle is at its equilibrium position. And then later you will have, when these particles, at the left end are at equilibrium, the quarter point are displaced to the left, 3/4 point are displaced to the right. At that point, you have maximum density and maximum pressure at the 2 ends, and the center has its lowest pressure. So what we've flipped between here is having maximum pressure at the center and minimum pressure at the ends versus minimum pressure at the center and maximum pressure at the ends. So the pressure is oscillating at its maximum right where the nodes are of this displacement wave. So here it is. It's shown are the displacement, delta x, standing wave, and in red, the pressure, P, standing wave. So you can see this is node, antinode, node, antinode, node, but the pressure has an antinode at the end, forced antinodes at the capped ends, and nodes where the halfway between the antinodes. And microphones are going to be measuring the red line here, the pressure. So this is a closed tube. And what are shown here are 3 different modes of standing waves. And the one you want to focus on actually is the one that's measured by your microphone in your experiment today, the pressure wave. So the m=1 has pressure antinodes at the ends, and it'll have a node right at the center. m=2 will have, again, antinodes at the ends an antinode in the middle, and then two nodes at the quarter and 3/4 points. And then the M equals 3 will have antinodes at the ends, two intermediate antinodes, and then all these nodes. And in each case, the lambda is 2L over M, where L is the length between the two ends. The frequency is M times V over 2L. V here is the speed of sound in air. And M is any integer, 1, 2, 3, and 4. If you have an open tube, this forces pressure nodes at the ends because those are open to the ambient pressure. But we will see that M equals 1, M equals 2, and M equals 3 follow the exact same equations. You have lambda M is 2L over M, frequency is M times V over 2L, and M can be any integer. So it turns out that actually mathematically a closed tube and an open tube produce the same harmonics. What's really different and interesting is an open closed tube, which is something you'll be using in your experiment this week. You'll open one end and the speaker at the other end forms a closed end. In this case, you form an antinode at one end and a node at the other. And what that means is that now lambda is 4L over M. So this is actually, the wavelength here is 4 times the length of this tube for the lowest mode. And then when you go to the next one, what happens is that now it's 3 times that frequency. So what we do is we still use this same equation, F equals M times this length, but now it's V over 4L. But what you do is you skip the even numbers. Only odd numbers of M are allowed for an open closed tube. And that should be enough for your theory and to prepare you for the pre-practical quiz this week. Okay.